Hello everyone, I'm Thaninian. Today I'm talking about phosphoric acid. Today we are covering where do we use phosphoric acid and matter of phosphoric acid and the structure and property of phosphoric acid and how we can connect to organic chemistry and thermochemistry, and also how we can talk about enthalpy change, also energy of rate of reaction. So exactly what is phosphoric acid? It's a molecular formula of H3FO2. Now this may look similar to phosphoric acid, but it's different. Also, where we can find phosphoric acid. So mainly we could find that in soft drinks and fertilizer. So mostly in South Asian countries they used as a fertilizer for agriculture lands. So now it may look similar, but the small pH bond is very important because it gives phosphoric acid to special properties like I mentioned it, fertilization for the plants. And second one is it can reducing agent, meaning it can donate electron during the chemical reaction. So let's start with some quick interesting fact about phosphoric acid. First, the chemical formula of phosphoric acid is H3FO3, not to be confused with H3FO2 from an earlier source. Be careful not to mix up them. The IUPAC name phosphoric acid, its commonly known name is orthophosphorus acid. So let's talk about what does it look like at a room temperature. It is a voice crystal is solid, similar to appearance of sugar, but definitely not something you should taste. Another important property is that it's a high solvent water, because I already mentioned it. They used in fertilization for the plants for agriculture land. So if you want to get into the plant tissues, so it can solve in water and it can go inside and give energy to the plant. So let's talk about other important fact about that. So what the most important feature about direct phosphorus hydrogen bond, also called pH bond. This bond makes a difference from a regular phosphoric acid and give it is special chemical properties. In a short, H3FO3 is white crystal solid, high soluble in water and contain a unique pH bond. So let's get into structure and properties of matter. So let's talk about Lewis structure of phosphoric acid, because this is where chemistry really start to make a sense. So let's start with how we phosphorus. So phosphorus comes in the middle and one double bond with oxygen, P double, like two lines O, and two single bond with OH group, POH, one single bond with hydrogen. The pH bond is very special, which makes I already mentioned it two properties. And let's talk about Vesper theory. The notation of AX3E, which means 3 bond atom and one lone pair of elements around the central atom. This gives molecular triangle pyramid shape similar to ammonia, because the lone pair, the molecular polar, meaning the charge is no evenly distributed. The hybridization of phosphorus is sp3, because there are 4 electron domain around the central atom. As for the intermolecular force, the OH group allow hydrogen bonding, which one of the strongest intermolecular force. This is one of the reason why phosphoric acid dissolve easily in water. Here's an example of Lewis structure and Vesper theory. The theory called triangle pyramid, because phosphorus come in the middle, which is P, and 3 oxygen like 3 times, and with the oxygen, H is one with the oxygen. Now let's get into organic chemistry, specifically functional group and the key reaction of phosphoric acid. The functional group in phosphoric acid is called phosphorate group, written as FO bracket OH2. This means the phosphorus atom is double bond to one oxygen atom and single bond to OH group. What makes this molecule special and different from many other phosphorus compound is the direct pH bond. This phosphorus hydrogen bond allow phosphoric acid to act as a reducing agent, meaning it can donate electron to other substance. Now let's look at the 3 reactions. So let's talk about how phosphoric acid is used to make an important fungicide called Polystyl AL. This is industrial application, meaning it can carry out larger scale of factories to help farmers to protect their crop. The reaction is acid-base neutralization. Here's what happened. Phosphoric acid react with aluminum hydroxide together, then follow aluminum phosphate and water. They balance a chemical equation. On the left side, H3FO3 is phosphoric acid, AlOH3 aluminum hydroxide which act as a base. On the right side, AlH2FO3 which aluminum phosphorate which active fungicide ingredient water which is harmless for the water. This reaction is used to produce volatile AL which applied to crop such as like potatoes, grapes and avocados to control the disease called Phytophthora root coat. Why is it important? Phytophthora root coat can destroy entire crops. Without volatile AL, farmers could lose hundreds of millions dollars every year. It also helps maintain food supply stability and food price from rising. So this single acid-base reaction plays major role in global agriculture and food security. Now let's talk about environmental oxidation. Phosphoric acid in the environment, phosphoric acid can slowly undergo oxidation and convert into phosphoric acid. The reaction is H3PO3 plus O. It become like H3FO4 plus HAO. This process can occur naturally in the soil and the water through exposure to oxygen, microgon and on other oxidation substance. The product formed in phosphoric acid which contain phosphorate ions. This phosphorate can act in a nutrient for plant and algae.
The phosphonate functional group makes phosphonic acid a good reducing agent. It is used in industrial synthesis for the fungicide Phocytil Al and is manufactured from phosphorus trichloride. Environmentally, it oxidizes to phosphoric acid, which acts as an algae fertilizer. The oxidation of phosphonic acid to phosphoric acid is an exothermic reaction. Calculations using standard heats of formation yield an enthalpy change of negative 38.0 kilojoules per mole. The oxidation of phosphonic acid is kinetically slow at room temperature, taking weeks or months. However, higher temperatures, soil microbes, and oxidizing agents like chlorine significantly speed up the reaction rate. Phosphonic acid has significant positive impacts, controlling crop diseases and saving hundreds of millions of USD annually. However, overuse leads to phosphorus accumulation, reduced soil biodiversity, and economic burdens for small farms. In the environment, phosphonic acid degrades to phosphate, leading to eutrophication and dead zones, like the large one in Lake Erie. Concentrated solutions are corrosive, requiring appropriate personal protective equipment, or PPE. However, diluted food residues are generally considered safe. At a personal level, phosphonic acid is in common lawn and rose sprays, contributing to eutrophication. Globally, it helps farmers in countries like India and Kenya, but lack of training leads to over-application and contamination, emphasizing the need for education and affordable application tools. Future advancements like slow-release fertilizers and precision agriculture using drones can significantly mitigate runoff and chemical use. Banning residential use can also eliminate unnecessary urban runoff, improving water quality.
If you have any questions, you can ask me. Thank you for listening my presentation. Now also, I want to add something. So we could use, I'm not against phosphoric acid in agricultural lands, but also I'm saying it helps so many people to get more money also for the basic families. So I'm like, we have to use as much we can, but not too much. It can affect the environment, but we could use it. Thank you for listening.